We've already discussed what is force, a push or a pull on an object. So our focus today then is how do those forces impact motion of some other type of object. And we're going to look at specifically balanced versus unbalanced forces, and also what is net force. And as we talk about net force, we're going to use a little symbol called sigma. Just keep an eye out for that. Now we know a force is a push or a pull on an object, and we measure that force at any time in a unit called newtons. Of course, after Sir Isaac Newton, who discovered gravity, right, came up for the formula for gravity. And like I mentioned, we're going to use the symbol sigma. It's kind of like a sideways M, or a really pointy capital E. But that is a shorthand representation of the word sum. And of course, in math, we know sum means total. So any time that we want to measure the total number of newtons acting on an object, we might see this sigma F, which is sum of forces. So keep an eye out for that on both assignments and a quiz. Now the purpose of taking the sum total of all forces on an object is to know the net force. And net force will really give us an idea if the object is in motion, not in motion, changing motion, staying constant. Net force really tells us what's happening specifically with the motion of an object. There's really two basics to know when we're calculating for net or total force. If the forces applied on an object are found to be in the same direction. What we do then to calculate net force is we simply add those forces together. While if a force is applied in an opposite direction, what we do then is subtract those forces. We subtract them from one another. So for example, over here with the horses, we've got the cart, and they're all pulling the cart in the same direction. Because they're all pulling in the same direction, I would then add all their forces together to figure out how many newtons are they using to pull the cart. So for example, if each horse was pulling with a force of 10 newtons, each horse was pulling with 10 newtons, well, there's 6 horses. So if I add them all together, 10, 20, 30, 40, 50, 60, I've got 60 newtons pulling that cart there. However, if the forces are applied in the opposite direction, like our tug-of-war game here, right, one team's pulling one direction, one team's pulling the other, I would then subtract those forces to figure out the total newtons. So if this team here was pulling with a force of 40 newtons and this team here with 30, subtracting them would tell me that the total newtons on the rope here would be 10, because I would subtract them from each other. Now once net force is calculated, I can determine if I'm dealing with either a balanced force or an unbalanced force. And balanced force is when I have two forces in the same strength. So I have the same force happening, but occurring in different directions. Well, I can see that example down below here. I've got the same amount of force on one side as I do on the other. Because they're going opposite directions, I would subtract them, giving my net force a total of 0, meaning I am completely balanced on one side compared to the other side. And when we see this occur, we really have no change in motion or velocity of the object. Okay, no change in motion or velocity. And net force, like we said, when it's balanced, is always equal to 0 newtons. balances out the force on one side compared to the other. They are equal. In the case of an unbalanced force, what's happening now is that forces are applied to an object in varied size and direction. So because the forces are varied in both size and direction, what we notice is that object likely has a change in motion or velocity. My net force is no longer 0. It's any number but 0, showing that there is not a balance to those forces any longer. We can see here I can have two ways of calculating net force. They can be going from the same direction and having the net force one way, or they can be opposite directions but different sizes, creating an unbalanced force in one direction. Now these forces are represented in something called a free body diagram. And to create a free body diagram, we always start with a box. And that box is representing the object that the forces are acting on. So in this case, our object what the forces are acting on here is this rope, right? All the people here are pulling on the rope. So the rope has forces acting on it, as we can see from the people. We've got a group pulling it in this direction, a group pulling it in this direction. So we want to place those arrows on the box showing the forces acting on the rope. So we've got a team pulling in this direction and a team pulling in this direction. And because they're the same amount of people, same size people, and we can see by the diagram here they are equal forces, I tried to make my arrows as close to the same size as I could. Both of these are an applied force, as is people pulling on the rope. But those aren't the only two forces acting on the rope here. We of course know that gravitational force is happening on the rope, force of gravity. And whenever I have a force of gravity in an object not falling downward, I also have to replace it with a normal force. Okay, and again, I try to keep those two arrows balanced because I know this rope isn't rising or sinking, right? It's staying consistent due to the motion of the people. So this is one example of a free body diagram. Another example of a free body diagram would be this girl on the skateboard. We've got to figure out what object do we want to use for our free body diagram to represent. With the square here, we know it most likely would represent the skateboard. Forces are acting on the skateboard here. So for starters, the graphic tells me that her direction of motion is this way. So that would be the applied force, that she pushed the skateboard in that direction. But because the skateboard is moving across a road, we know there's some friction happening with the tires as well. But because she is moving, I know the friction force must be smaller than that applied force to keep her in motion. If the friction and applied force were the same amount, she would not be moving on her skateboard. Now again, because the skateboard is on the flat surface, I know there is definitely a force of gravity that is balanced out with a normal force, as the skateboard is on the Earth's surface. By completing this free body diagram, we're able to tell if the object is accelerating. And typically when we think of the word acceleration, we're thinking just of an object moving faster. But officially, the acceleration definition has three parts. A change in speed either to the positive, so speeding up, a change in speed to the negative, slowing down, or a change in direction. So increase in speed, decrease in speed, or a change in direction, those all indicate that the object has a change in motion. And we figure out if there's a change in motion or an acceleration by looking at that total amount of force or the net force after adding up that free body diagram. So thinking about our new definition of acceleration, look at this example. Got a picture of a car, right? So we're seeing the car inside the driver's seat. We got three things that we're looking at: the gas pedal, the brake pedal, and the steering wheel. And we want to figure out which of these would be considered an accelerator. So first we have to think about what each one does. Gas pedal causes the car to, of course, speed up. Brake pedal, of course, causes the car to slow down, while the steering wheel causes the car to turn or change direction. So knowing that's what each of those does, we have to figure out then, would that be an acceleration? Well, with our new definition, does speed up count as acceleration? You bet it does. It's kind of our typical thought. But brake pedal causing it to slow down, is that an accelerator? According to our official scientific definition, yes it is. Slowing down is still considered an acceleration, as is turning or changing direction. So all three of these parts of the car are considered an accelerator. So on the right hand side we have just a little checklist to think about. Which of the following would be considered an acceleration? Again, thinking about our definition, it has those three parts. So remembering those three parts, go through this list and check any that would be considered to be an acceleration. An object starting at rest and moving, so going from not moving to moving. An object that's speeding up. An object slowing down. Or an object changing direction. So check off which of the following would be an acceleration. So finally, now that our notes are complete, we have a few practice problems to complete. So there are practice problems 1 through 14 connected to this. There's no summary questions, just some practice. There's a few definition, there's a matching, and then you're going to see a lot of those free bodies. Some you have to calculate, and some you need to create. So think carefully, go back to the notes, go back to your FET practice, do what you need to do to get those ready to roll. Thank you.